So we'll begin lesson 10.5 today. It's on tangents. So we'll obviously begin with what is a tangent and look at the basic concept of tangent lines to circles. Some of the key, parts that make up a line that's tangent to a circle, and we'll look at some properties that we know to be true when a line is tangent to a circle, and then how we can solve some basic problems involving those. Okay, so let's start out with the definition of a tangent line to a circle. So a line is tangent to a circle, or segment could be tangent to the circle, if it intersects the circle in exactly one point and doesn't contain any other points on the interior of the circle. Okay, so it's got to be a line that just touches the edge of a circle. And obviously, it can't pass through the circle or be touching the circle at 2 points like a chord does. So this has just got to kind of glance off the side of the circle and hit it in just one spot. And that spot that it hits the circle in is called the point of tangency. All right. And if I show you an example here, you can see that line AB would be our tangent line, and it's tangent to circle C, and the point of tangency here is point A. So this line AB is just nicking the circle right here at this one singular point. All right. And obviously, that's the only point that the line and the circle have in common here is point A. So that's a tangent line, or it could be a segment. It doesn't have to be a line, it could be segment AB. All right. Now, one thing they'll ask us today is identify what we call common tangents. And we don't do a lot with this aside from finding it, understanding what it is, and being able to name like how many there would be given an example. And basically, a common tangent can be a line or a segment that's tangent to two circles in the same plane. So it's a line of tangency to two circles at the same time. So, for example, this set of circles, circle F and circle G. Now, the unique part of this one is it appears that the two circles have a single point in common. So they're really, really close to each other and just touch at one point. Okay. This line L would be considered a common tangent. Is tangent to both circle F and circle G at the same time. Okay. That's what we mean with a common tangent. Now, there actually are two other ones in this drawing that they don't have listed. There could be another common tangent that would be up top here and just touch both circles at once. And there would be a third one down here that could be drawn right here and just touch each of those circle once. So this example actually has three total common tangents that could be drawn in it. Okay. Another example would be this circle F, circle G again, but now they're obviously separate from each other. These two circles have no points in common, but we can draw a tangent line that would be tangent to both of them. So this line L coming down through here is just nicking circle F here and circle G here. So it's a tangent line to both of these circles. Okay, there's actually three more. There's another one we could draw kind of on the other angle on the inside here that would just nick them both. There's one on the top, one on the bottom. So there would be a total of four common tangents in this particular drawing. All right, so a lot of times they're going to ask us, how many common tangents are there? And it'll be our job to figure out how many we could draw in a particular situation. Okay, now looking at the theorems, see, these are what we're going to use to actually simplify and solve some problems that involve tangent lines. Okay, our first theorem is the one we use a lot, obviously the most. And it says that a line is tangent to a circle if and only if it's perpendicular to a radius drawn to that point of tangency. Okay, so what you should see here, hopefully, number one, is that this is a biconditional statement. If and only if means you can switch the hypothesis and conclusion of this, and it's true. So basically, we could say if a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. Or we could say um, if the line of tangency connected to the radius is perpendicular, then it has to be a tangent line. Okay, so here's the example. Here's circle S, okay, and here's line L, and it's perpendicular to the point of tangency. So this radius ST is perpendicular to line L. That's a right angle right there. Therefore, this line has to be tangent. Okay, so we can say it either way here. We could say if line L is tangent to the circle, then it's perpendicular to this radius. Okay, or we could say, oops, got this a little out of order. If line L is perpendicular at the point of tangency, then it has to be tangent. Okay, so we can actually do that one in either direction. Okay, so we're going to work a lot on the if we draw a radius from the center to the point of tangency, we know that it's a right angle, and that's going to let us solve a lot of problems using some other facts that we've had. All right, the other theorem here says that if two segments from the same exterior point are tangent to a circle, then they have to be congruent, the same length. So here we're looking at circle D. A and C are points of tangency that have extended from point B. So point B has to be at, your point has to be on the exterior of the circle. So point B is out here. We're saying that B to A is tangent to the circle, and BC is tangent to the circle. Okay. C and A are the points of tangency for each of those. Therefore, we know A to B and C to B have to be the same length. So that's what we're saying. If AB and CB are tangent and B's on the exterior, then AB and CB have to be the same length. They're congruent to each other. So that's a real simple one to use. Okay. So the first type of question you get tonight is identify the common tangents. If there are any common tangents, name how many, draw them in, and if no common tangent could exist, then just state that. Okay, so looking at our first example, okay, I have one common tangent I could draw on here, and I have a second one I could draw here. Okay, I can't draw one down through here because I'm not going to intersect both circles at only one spot. So this is a new one for us to see here, and there are only two common tangents. In our second example, I could have one up top here, I could have one on the bottom, and I could have one going through because of the circles just meet at one point right here. We're making that assumption, I guess, but that's the way it's drawn. And so now we know these have three common tangents. And this is an example, the last one here, where there are no common tangents. I could draw a bunch of, obviously, an infinite number of tangent lines on the outside circle, but all of the tangent lines on the outside won't come anywhere near the inside circle. And any one I draw on the inside circle are going to intersect the outside circle at 2 points. So there's no line I could draw that would intersect these two circles at only 1 point. All right, that's a little bit about common tangents. All right, next thing we'll do is get into using our theorem. And this is the most basic application of it. So what it's telling us here is that AB is a radius of the circle. We're supposed to figure out, is BC tangent to this circle? All right. So if BC is going to be tangent to the circle, then it's got to form a 90-degree angle. CBA has got to be a 90-degree angle because a tangent line always has to be perpendicular, which means 90 degrees to a radius with the point of tangency. So the way we're going to simply prove if BC is a tangent line or not is to see whether or not this triangle, ABC, is a right triangle. All right, so we're going to use Pythagorean theorem. And if this is a right triangle, then BC is tangent. If it's not a right triangle, then BC is not tangent. Okay. Now, the one thing you got to look out for with these problems is this 6 that was given here is only the distance from the circle to point C. See, notice that A to B is a radius, and that's 9. A to the edge of the circle is not included in this distance for AC. Okay, so you got to understand that AC is actually going to be the radius of 9 plus the exterior piece 6. So AC is actually 15. They do that quite a bit where you have to kind of catch that number right there. Okay, AC is also going to be, if ABC is our right angle, then AC is our hypotenuse. So when we go to set up our Pythagorean theorem, it's going to be 9 squared plus 12 squared equals 15 squared. AB and BC are the legs. They're the sides of the triangle that make the right angle. And AC is the hypotenuse. So the question is this true? So 81 plus 144 equals 225. If you square each of those numbers, 225 equals 225. That means, yes, this is a right triangle. So ABC is a right triangle, which means that BC is perpendicular to AB, makes a right angle. Therefore, BC is tangent to circle A at point B. Okay, so it was all about being able to prove that was a right angle. And if it's a right angle, then BC's got to be perpendicular to AB, which makes it tangent. So that's one of the first types of questions you get. Okay. Um, Now, this question, again, well, not again, but make sure you read the directions carefully. See, this one is telling you it is tangent. There's no question. QS is tangent to this circle and it's tangent at point Q. So I know QS is tangent, and I know that I know angle RQS has got to be a right angle. Okay, because that's the property that we had. Okay, so because we know QS is tangent to circle R at point Q, we know that RQS has got to be 90. So therefore, we know that this triangle RQS has got to be a right triangle. All right, so that's how we're going to find our value of x. We're going to be able to use Pythagorean theorem with the concept of this right triangle to be able to find the value of x. One thing to note again is that the distance from R to S total is the radius, which is unknown, it's x, plus the distance from the edge of the circle to S, which is 2. So RS is going to be x plus 2. So when we set up our Pythagorean theorem, it's going to be x squared plus 4 squared equals the quantity of x plus 2 squared. Now, what do we do with a binomial squared? We got to FOIL it. It's got to be x plus 2 times x plus 2. First outside, inside, last. Simplify. We should all get x squared plus 16 equals, and we get x squared plus 4x plus 4. That's when I take the quantity of x plus 2 and FOIL it, I get this answer. Okay, now subtract x squared from both sides and the x squareds cancel. Subtract 4 and we're going to get 12 equals 4x. X equals 3. And we got it. Okay, so that asks us to find the value of x. The value of x is 3. So that radius of this circle then now we know is 3. Now they could follow it up with what's the circumference of the circle, what's the area of the circle, because now we're armed with the fact that we know the radius is 3 and we can apply it to any other questions they want to ask. Okay. Another one of the same style of questions. Uh, Again, read the directions carefully or read what's given carefully. BC is tangent. So there's no question whether it's tangent or not. Since BC is tangent, you know that ACB is a right angle. Okay, it got to be because AC is a radius, BC is tangent. That's the point of tangency. That's got to be a right angle. Okay, so we know that ACB is a right triangle. I'm going to use Pythagorean theorem to find the missing value. Now, notice in this one, they're not making you add to get the full length of AB. They're telling you the full length is marked out to be 17. So we got x squared plus 14 squared equals 17 squared. Okay. X squared plus 196 is 289. Subtract 196. X squared is 93. Now, let me jump up here again. It said find the value of x to the nearest hundredth. That's a pretty nice clue that something's going to happen a little different. So x squared equals 93. We got to take the square root of both sides. That's what cancels out the square on the x. Remember, square root cancels the square. Square root of 93 rounded to the nearest hundredth, 9.64. Oops. That should just say x equals. That's my mistake. X equals 9.64. That's our answer. Okay. So eliminate that. All right, that's another style of question. Okay, the last type of question is dealing with the fact that if I have a point on the outside of the circle and I have a set of tangent lines back to the circle, the tangent lines have to be the same length. Okay, so this is set up like this. A photographer wants to take the picture of the local fountain. There's your photographer standing at point A, obviously on the exterior of that circle. She positions herself so that, at point A so that the fountain can be centered in the picture. It says AB and AC are tangent to the fountain. Find the lengths of the tangents and find the length of AB. All right, so we just use our basic property because AB and AC are tangent to the circle and they're from the same exterior point. We know that these two are the same length. So we know 7x minus 9 equals 5x plus 5. Subtract the 5x, add a 9, divide by the 2x is 7. Guys, make sure you answer the questions here. Find AB. So we got to find the distance from A to B. Well, they're the same, but we're asked to find the distance of AB. So we're going to say, all right, AB is 7 times our x value, which is 7 minus 9. 49 minus 9 is 40. So there's our solution. Make sure we answer questions. Okay, so that's what we got today on tangents. We're going to add a little bit more to it tomorrow, some different things we can do. But those are the few basic properties that we've had. Your homework tonight, make sure you get it done. Write these problems out so you can see them. I think it's very helpful for you to write it down. I know I don't necessarily see your work, but it will help you see the concepts and understand it better. All right, I'll let you get to work.